There's something in the universe you can see but never reach, a boundary that retreats faster than you can chase it. Imagine boarding the fastest spacecraft ever built, accelerating until galaxies blur past like raindrops on a windshield. You travel for millions of years, then billions. You've crossed distances that dwarf human comprehension, and yet something impossible is happening. The edge isn't getting any closer. Today, we're going to uncover why the edge of the universe isn't just unreachable. It's a concept that shatters everything you thought you knew about space, time, and existence itself. If you're fascinated by the deepest mysteries of our cosmos and want to journey with me to the frontiers of human knowledge, make sure to subscribe to this channel and give a thumbs up. And here's something I've been wondering. If you could ask the universe itself one question and receive a definitive answer, what would you ask? Let me know in the comments down below. I will pin the most creative answer. Now let's begin. To understand why we can't reach the universe's edge, we first need to grasp what we mean by the universe and what an edge would even look like. When most people picture the universe, they imagine a vast but finite bubble floating in some larger space with a boundary we could theoretically reach if we traveled far enough. But this intuition, as natural as it feels, misunderstands the very nature of space itself. The universe isn't a thing inside space, it is space. It's not expanding into anything. Space itself is stretching, carrying galaxies along like raisins in rising bread dough. The observable universe, everything we can possibly see, extends approximately 46.5 billion light-years in every direction from Earth. You might immediately notice something odd about that number. If the universe is only 13.8 billion years old, how can we see objects 46.5 billion light-years away? Shouldn't light have only had time to travel 13.8 billion light-years? This puzzle reveals our first clue about why reaching an edge is impossible. The space through which that light traveled has been expanding the entire time, stretching the distance between us and those distant objects. The Hubble Space Telescope, launched in 1990, revolutionized our understanding of cosmic distances and expansion. By observing distant galaxies and measuring how their light has been stretched, a phenomenon called redshift, astronomers confirmed that the universe is expanding in all directions. The Planck satellite, which operated from 2009 to 2013, mapped the cosmic microwave background radiation with exquisite precision, giving us our most accurate measurements of the universe's age, composition, and expansion rate. But here's where things get truly strange. The universe isn't just expanding, it's accelerating. In 1998, two independent teams studying distant supernovae made a shocking discovery that would earn them the 2011 Nobel Prize in Physics. They found that galaxies aren't just moving away from us, they're moving away faster and faster. Something is pushing the universe to expand at an ever-increasing rate, and we call this mysterious force dark energy. Dark energy makes up approximately 68% of the universe's total energy density, yet we have no idea what it actually is. It's not matter, it's not radiation, and it doesn't clump or cluster like ordinary matter or even dark matter. It appears to be a property of space itself, a kind of intrinsic energy that permeates every cubic centimeter of the cosmos. As space expands, more space comes into existence, and with it, more dark energy. This creates a runaway effect where expansion drives more expansion. The James Webb Space Telescope, which began operations in 2022, is now peering deeper into space and further back in time than ever before, observing galaxies as they appeared just a few 100 million years after the Big Bang. These observations help us understand how the universe evolved from a hot, dense state to the vast, cool cosmos we inhabit today. But they also reinforce a sobering truth. The deeper we look into space, the more we see evidence of an expanding universe that has no center and no edge that we could ever reach. let's confront the first major barrier to reaching the universe's edge, the cosmic horizon. Just as Earth's horizon limits how far you can see across the ocean, the universe has its own horizon determined by the speed of light and the age of the cosmos. Light travels at approximately 299,792 kilometers per second, the universe's ultimate speed limit according to Einstein's special relativity. Nothing with mass can reach this speed, and no information can travel faster than light. Since the universe is 13.8 billion years old, you might think we could only see objects whose light has been traveling for 13.8 billion years, placing them 13.8 billion light years away. But remember, space has been expanding this entire time. The most distant objects whose light is now reaching us emitted that light when they were much closer to us. Over billions of years, space stretched, carrying those objects away while their light was in transit. The objects that emitted the cosmic microwave background radiation, the oldest light we can detect, are now about 46.5 billion light-years away. This boundary, the edge of the observable universe, isn't a physical barrier in space, it's a horizon in time. Beyond this distance, we're looking back to before the universe became transparent to light, just 380,000 years after the Big Bang. Before that moment, the universe was so hot and dense that photons couldn't travel freely. They constantly scattered off charged particles in an opaque plasma. We can't see beyond this veil with telescopes, no matter how powerful, because there are no photons from earlier times. But let's imagine you could somehow travel toward this horizon. You board a spacecraft and head toward the most distant galaxy we can observe, one whose light has been traveling for over 13 billion years. Even if your ship could travel at 99.9% the speed of light, which is impossibly fast given our current technology and understanding of physics, you would encounter an insurmountable problem. That galaxy isn't sitting still waiting for you. It's racing away from you as space itself expands between you. The Hubble constant, measured most recently by the Planck mission at approximately 67 kilometers per second per megaparsec, tells us how fast the universe expands. This means that for every megaparsec, about 3.26 million light-years of distance between you and another object, the space is expanding at an additional 67 kilometers per second. Nearby galaxies recede slowly, but sufficiently distant galaxies recede faster than light itself. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Space itself is expanding between us. There's a critical distance called the Hubble radius, currently about 14.4 billion light-years away, beyond which objects recede from us faster than light. Anything beyond this distance is, in principle, unreachable even if you could travel at light speed, because space is expanding faster than you can traverse it. It's like trying to swim against a current that's flowing faster than you can swim. You'll never make forward progress no matter how hard you try. Speaking of the incredible barriers to cosmic travel, if you're curious about why even reaching planets within our own solar system presents nearly insurmountable challenges, check out my video "This is Why We Will Never Reach Other Planets," where we explore the sobering realities of space travel even in our cosmic backyard. The link is in the description below. Now let's continue examining why the universe's edge remains forever beyond our reach. The cosmic event horizon represents an even more fundamental barrier than the Hubble radius. Due to accelerating expansion driven by dark energy, there's a boundary approximately 16 billion light-years away beyond which events happening now will never become visible to us, no matter how long we wait. Light emitted from beyond this horizon will never reach us because space expands too quickly for it to make progress toward us. This horizon effectively defines the ultimate limit of what's causally connected to us. the maximum extent of the universe we could ever observe or influence. What makes this particularly poignant is that this horizon is shrinking in a sense. As the universe accelerates, galaxies that we can see today will eventually cross this event horizon and disappear from view forever. They won't suddenly vanish, they'll gradually redshift toward invisibility as their light gets stretched to longer and longer wavelengths until it becomes undetectable. Future civilizations trillions of years from now will live in a lonelier universe, able to see only their local galaxy cluster while the rest of the cosmos fades beyond the horizon. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will survey vast regions of the sky to map dark energy's effects over cosmic history. These observations will help us understand whether dark energy's strength changes over time and what the ultimate fate of the cosmic horizon might be. But regardless of what we learn, the fundamental barrier remains. Accelerating expansion ensures that vast regions of the universe are forever beyond our reach. Now let's consider the second major barrier, the nature of space itself. When we talk about the universe having no edge, we're making a statement about its topology, its overall shape and structure. Current observations suggest the universe is geometrically flat on the largest scales, meaning that parallel lines stay parallel and the angles of triangles add up to 180 degrees, just like in Euclidean geometry you learned in school. But flat doesn't necessarily mean infinite. Consider the surface of a cylinder. It's flat in the sense that you can draw triangles whose angles sum to 180 degrees, yet it's finite. You could walk around it and return to your starting point. Similarly, the universe could be flat yet finite if it wraps around on itself in higher dimensions. This is difficult to visualize because it requires imagining three-dimensional space curving through a fourth spatial dimension. The cosmic microwave background observations from the Planck satellite have searched for evidence of such topology. If the universe wrapped around on itself on scales smaller than the observable universe, we might see repeating patterns in the cosmic microwave background, like looking in a hall of mirrors. No such patterns have been found, suggesting that if the universe is finite, it's much larger than the observable portion. But we can't rule out the possibility that it's truly infinite. If the universe is infinite, then the concept of an edge becomes meaningless. There's no boundary because space extends forever in all directions. You could travel for eternity and never run out of universe to explore. Every direction is the same as every other. There's no special place or direction that represents toward the edge. The universe has no center and no boundary, just endless space filled with galaxies, clusters, and cosmic web structures repeating in statistical patterns forever. But if the universe is finite yet unbounded, wrapped around on itself, the situation is equally strange. You could travel in what seems like a straight line and eventually return to your starting point, like an ant crawling around a balloon's surface. But you still wouldn't encounter an edge. There would be no barrier, no boundary, no place where space ends. You'd simply find yourself tracing geodesics through curved space, returning endlessly to the same regions. The Sloan Digital Sky Survey, which has mapped over 3 million cosmic objects, reveals large-scale structures, galaxy filaments and voids, that repeat in statistical patterns. These observations help constrain the universe's possible topology. If the universe repeated on scales we could observe, we'd see correlated patterns in galaxy distributions. The absence of such correlations pushes any potential cosmic wraparound to scales larger than the observable universe, beyond what we can ever directly detect. Let's explore the third barrier to reaching the universe's edge: the fundamental nature of space-time itself. Einstein's general relativity, published in 1915 and confirmed by countless experiments since, teaches us that space and time are not separate, absolute entities, but are woven together into a four-dimensional fabric called spacetime. Mass and energy curve this fabric, and objects follow the straightest possible paths through curved spacetime, paths we perceive as orbits and trajectories. What does this mean for our quest to reach an edge? It means that space isn't a passive container holding matter, it's an active, dynamic participant in cosmic evolution. The Big Bang wasn't an explosion in space, it was an explosion of space itself. Every point in the universe was at the Big Bang, because the Big Bang happened everywhere at once. There was no center, no special location from which everything expanded. Space itself came into existence and immediately began expanding. This leads to a profound realization. Asking what's beyond the edge of the universe is like asking what's north of the North Pole. The question seems to make sense grammatically, but it's actually meaningless. Just as north is a direction defined by Earth's surface, and you can't go more north than the North Pole, the universe defines what space means, and there's no meaningful outside or beyond to speak of. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, which made its first detection of gravitational waves in 2015, has opened an entirely new window on the cosmos. Gravitational waves are ripples in spacetime itself, created when massive objects like black holes or neutron stars spiral together and merge. These detections confirm Einstein's prediction that spacetime is a physical entity that can flex, ripple, and wave. Understanding spacetime as a dynamic fabric rather than a static stage fundamentally changes how we think about cosmic boundaries. The European Space Agency's LISA mission, planned for the 2030s, will detect gravitational waves from space, observing mergers of supermassive black holes and potentially even signatures from the early universe. These observations might reveal whether spacetime has exotic properties we haven't yet discovered, perhaps extra dimensions curled up at microscopic scales, or quantum foam at the Planck length, where space and time become granular rather than continuous. String theory and loop quantum gravity, two competing approaches to quantum gravity, both suggest that spacetime might not be fundamental, but rather emergent from deeper quantum structures. If space is built from discrete quantum units at the Planck scale, about 10 to the negative 35 meters, then concepts like edge and boundary might not even apply to the universe's deepest level. Space might be more like a fabric woven from quantum threads, and asking about its edge is like asking where the pattern in a tapestry ends when the tapestry itself is infinite. The fourth barrier brings us to cosmic inflation, a brief period of exponentially rapid expansion that occurred in the universe's first fraction of a second. Proposed by physicist Alan Guth in 1980 and refined by many scientists since, inflation solves several puzzles about the universe's large-scale properties. It explains why the cosmic microwave background has nearly the same temperature in all directions, why the universe appears geometrically flat, and why we don't observe exotic relics like magnetic monopoles. During inflation, which lasted from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26, and possibly much more. A region smaller than an atom swelled to larger than the observable universe today, all in a time span shorter than a blink. This exponential expansion stretched any pre-existing curvature to flatness and spread quantum fluctuations across cosmic scales, seeding the formation of all structures we see today. Here's why inflation creates a barrier to reaching an edge. If inflation happens, then the observable universe represents only a tiny fraction of the whole. Most of the universe lies beyond our cosmic horizon, forever inaccessible. The regions we can observe emerged from an infinitesimal patch of the pre-inflation universe. Everything beyond our horizon came from different patches that inflated separately and are now causally disconnected from us. No signal can travel between them because space expanded too rapidly. The Planck satellite's measurements of the cosmic microwave background beautifully match inflation's predictions. Tiny temperature fluctuations, variations of 1 part in 100,000, show the exact statistical pattern expected from quantum fluctuations stretched by inflation. These observations don't prove inflation conclusively, but they provide strong supporting evidence. The BICEP and Keck array experiments at the South Pole search for even subtler signatures, primordial gravitational waves that inflation should have generated. If inflation occurred, the universe beyond our horizon could be vastly, perhaps infinitely, larger than what we observe. Some inflation models suggest eternal inflation, where different regions stop inflating at different times, creating an infinite mosaic of pocket universes. Each pocket could have different physical properties, different fundamental constants, even different numbers of dimensions. Our observable universe would be just one bubble in an eternally inflating multiverse. Whether or not the multiverse exists, inflation ensures that the vast majority of space lies forever beyond our reach. The cosmic horizon isn't just a limitation of our telescopes or our travel speed. It's a fundamental boundary carved into the structure of reality by the universe's explosive birth. No future technology, no matter how advanced, can overcome this barrier because it's written into the initial conditions of space-time itself. The fifth barrier involves the ultimate cosmic speed limit, the speed of light in vacuum. Einstein's special relativity, published in 1905, revolutionized physics by showing that space and time are relative. They depend on the observer's motion. But one thing remains absolute for all observers: the speed of light, approximately 299,792.458 kilometers per second. Nothing with mass can reach light speed because doing so would require infinite energy. As objects accelerate, they gain kinetic energy, but relativity shows that this energy manifests as increased mass. The faster you go, the more massive you become, requiring ever more energy to accelerate further. At 99% light speed, you'd have more than 7 times your rest mass. At 99.9%, more than 22 times. The curve approaches infinity as you approach light speed, creating an insurmountable barrier. Particle accelerators like the Large Hadron Collider at CERN routinely demonstrate this limit. Physicists accelerate protons to 99.999991% light speed, so close to light speed that the protons traverse the 27-kilometer ring over 11,000 times per second. Yet despite pumping enormous energy into these particles, each proton carries as much kinetic energy as a flying mosquito, compressed into something trillions of times smaller. They never quite reach light speed. The universe enforces its speed limit absolutely. Even if you could somehow reach light speed, strange things happen to space and time. Time dilation becomes infinite. From your perspective, the journey would take 0 time, while the external universe ages infinitely. Length contraction also becomes infinite. Distances in your direction of travel shrink to 0. You'd experience the universe as infinitely compressed in front of you. These aren't just theoretical curiosities, they're fundamental aspects of how space-time works. GPS satellites must account for time dilation to maintain accuracy, and particle physics experiments routinely observe these effects. The speed of light doesn't just limit how fast you can travel, it limits how quickly information can propagate. Causality itself depends on this speed limit. If information could travel faster than light, you could theoretically send messages into your own past, creating paradoxes. The universe seems carefully constructed to prevent such contradictions. The cosmic speed limit protects causality, ensuring that cause precedes effect, and that the universe maintains logical consistency. This creates a profound implication for cosmic exploration. Even if you could travel at light speed, which you can't, reaching distant cosmic horizons would take billions of years as measured by external observers. And remember, the universe keeps expanding while you travel. By the time you reached what was once the horizon, it would have receded further. You'd be chasing a finish line that moves away faster than you can approach it. It's an unwinnable race written into the laws of physics. The Breakthrough Starshot initiative, announced in 2016, aims to send tiny spacecraft to Alpha Centauri, our nearest stellar neighbor, at 4.37 light-years away, at 20% light speed, using powerful laser arrays. Even at this tremendous velocity, the journey would take about 20 years. Reaching galaxies millions or billions of light-years away at such speeds would require time frames vastly exceeding the current age of the universe. The speed of light barrier makes intergalactic travel impractical even before we consider the cosmic expansion working against us. Now we encounter the sixth barrier, the arrows of time and entropy. The second law of thermodynamics states that entropy, disorder, or randomness always increases in closed systems. This law gives time its arrow, distinguishing past from future. You can scramble an egg but not unscramble it, break a glass but not spontaneously reassemble it. Entropy marches inexorably forward, and with it, the universe evolves toward equilibrium. Over cosmic timescales, this has profound implications. Stars will eventually exhaust their fuel, galaxies will radiate away their energy, black holes will evaporate through Hawking radiation, and the universe will approach maximum entropy, a state called heat death. Current estimates, based on dark energy observations and thermodynamic calculations, suggest this final state lies inconceivably far in the future, perhaps 10 to the 100 years from now, a 1 followed by 100 zeros. What does this mean for reaching the universe's edge? It means that even if you could somehow overcome all other barriers, you'd face a fundamental limit imposed by time itself. Any journey to cosmic horizons would take so long that the universe would evolve dramatically during your travel. Stars would die, galaxies would merge, and the cosmic landscape would transform beyond recognition. You wouldn't just be traveling through space, but through epochs of cosmic evolution. The heat death scenario represents a kind of temporal edge to the universe, not a boundary in space, but a limit in time beyond which the universe reaches a final, unchanging state. All temperature differences will equalize, no energy gradients will exist to power complex processes, and nothing interesting will happen ever again. The universe won't end in a bang or a crunch, but in an eternal whisper of maximum entropy darkness. But even this isn't quite an edge in the traditional sense. The universe would still exist, still extend through space, still contain its full complement of matter and energy, just arranged in the most probable, most disordered configuration. Space wouldn't end. It would simply be filled with a thin, cold bath of radiation and the occasional particle, spread uniformly across infinite volumes. The heat death is less an ending than an eternal plateau. Roger Penrose has proposed an alternative called conformal cyclic cosmology, suggesting that the heat death of one cosmic aeon becomes the Big Bang of the next. In this view, the universe cycles eternally, with each infinite future connecting to a new beginning. Whether this scenario is correct remains speculative, but it illustrates that even the ultimate fate of the universe might not represent a true ending, merely a transition to a new phase of existence. The seventh barrier brings us to the nature of observation itself. Quantum mechanics, confirmed by countless experiments since the early 20th century, reveals that observation fundamentally affects reality at the smallest scales. The Heisenberg uncertainty principle tells us that certain pairs of properties, like position and momentum, cannot be simultaneously known with arbitrary precision. The more precisely you measure one, the more uncertain the other becomes. What does this have to do with reaching the universe's edge? It reminds us that the universe isn't just a stage we observe from the outside, we're participants embedded within it. Every observation, every measurement, every journey we undertake involves interaction with the cosmos. We can't stand apart from the universe to view it objectively because we're made of the same stuff, governed by the same laws, woven into the same causal fabric. The concept of the edge itself might be observer-dependent. Different observers moving at different velocities will disagree on simultaneity. Events that appear simultaneous to one observer happen at different times for another. This relativity of simultaneity, a consequence of Einstein's theory, means that different observers would define the cosmic now differently. Your cosmic horizon differs from that of an observer in a distant galaxy moving at high velocity relative to you. The Wheeler-DeWitt equation, an attempt to apply quantum mechanics to the entire universe, suggests that time itself might be emergent rather than fundamental. In this view, the universe doesn't evolve through time. Rather, time emerges from correlations between different parts of the universal quantum state. If time isn't fundamental, then concepts like reaching and traveling become ambiguous. How do you journey to an edge when the very notion of a journey presupposes time that might not fundamentally exist? The holographic principle, emerging from black hole physics and string theory, suggests that all the information in a volume of space can be encoded on its boundary surface. This radical idea implies that our three-dimensional universe might be a projection of information encoded on a two-dimensional cosmic horizon. If true, the universe might not have the dimensionality we perceive, and the concept of an edge becomes even more ambiguous. These quantum and information theoretic considerations remind us that the universe is stranger than we imagine, perhaps stranger than we can imagine. Our intuitions, evolved to navigate medium-sized objects at everyday speeds on Earth's surface, fail when confronted with cosmic extremes. The universe's edge might not be the kind of thing that could ever make sense to minds like ours, constructed as we are from biological matter shaped by terrestrial evolution. The eighth barrier involves dark matter and dark energy, the universe's dominant components, yet ones we barely understand. Dark matter, making up about 27% of the universe's energy density, reveals itself only through gravitational effects. Galaxies rotate too fast for their visible matter. Galaxy clusters bend light more than their stars and gas can account for, and large-scale structure formation requires more gravity than ordinary matter provides. The Vera C. Rubin Observatory, beginning operations in the mid-2020s, will survey the entire southern sky repeatedly, mapping billions of galaxies and measuring how their light is bent by dark matter's gravity. These observations will create the most detailed three-dimensional map of dark matter ever made, revealing how it structures the cosmic web and guides the formation of galaxies and clusters. But we still don't know what dark matter is. Leading candidates include WIMPs, weakly interacting massive particles, and axions, hypothetical particles proposed to solve other physics problems. Experiments deep underground and in space search for these particles, but decades of searching have yielded no definitive detections. Dark matter might be something entirely unexpected, perhaps even indicating a need to modify our understanding of gravity itself. Dark energy presents an even deeper mystery. Making up 68% of the universe, dark energy drives cosmic acceleration, yet we have no compelling explanation for its nature or origin. Is it Einstein's cosmological constant, a property of empty space itself? Is it a dynamic field called quintessence that varies over time and space? Or does it indicate that general relativity breaks down on cosmic scales, requiring modification? The Dark Energy Spectroscopic Instrument, or DESI, which began observations in 2021, is measuring the expansion history of the universe across 10 billion years by mapping millions of galaxies. These observations will help determine whether dark energy's strength changes over time, potentially discriminating between different theoretical models. The European Space Agency's Euclid mission, launched in 2023, complements this work by mapping dark matter and dark energy's effects across a third of the sky. Why does this matter for reaching the universe's edge? Because dark matter and dark energy dominate the universe's structure and evolution. Dark matter's gravity creates the cosmic scaffolding on which galaxies form. Dark energy determines the universe's ultimate fate and defines the cosmic event horizon. We're trying to reach an edge in a universe whose dominant components we don't understand, like navigating a ship when we can't see the ocean or feel the wind. Moreover, dark energy ensures that the cosmic horizon is dynamic, not static. As dark energy drives accelerating expansion, more galaxies cross the event horizon, disappearing from our potential reach. The edge, in this sense, is moving toward us, not because space has a boundary approaching us, but because the sphere of causally connected space is shrinking. In the distant future, observers will live in increasingly isolated island universes, unable to observe or reach regions that we can see today. The ninth barrier emerges from the anthropic principle and the possibility of a multiverse. The anthropic principle observes that the universe's properties must be compatible with the existence of observers, because otherwise we wouldn't be here to observe them. This seemingly trivial observation has profound implications when combined with theories suggesting multiple universes with varying properties. Eternal inflation, mentioned earlier, suggests that different regions of space stop inflating at different times, creating pocket universes, bubbles within the eternally inflating cosmic foam. Each bubble might have different values for fundamental constants, different particle masses, even different numbers of dimensions. Most of these bubbles would be inhospitable to life as we know it, but some, like ours, would have just the right properties for stars, planets, chemistry, and eventually observers. String theory, attempting to unify quantum mechanics and gravity, predicts a vast landscape of possible vacuum states, perhaps 10 to the 500 or more distinct configurations. Each configuration represents a different possible universe with its own laws of physics. If both string theory and eternal inflation are correct, the multiverse might contain every possible variation of physical law, with our universe being just one island in an infinite archipelago. Here's how this creates a barrier. If pocket universes exist beyond our cosmic horizon, each with potentially different physics, then the concept of reaching the edge becomes meaningless. You can't travel between bubbles because they're separated not just by vast distances but by regions of space still undergoing inflation. The exponentially expanding barrier between bubbles grows faster than light can cross it, forever isolating each pocket universe from its neighbors. The collision between bubble universes might leave observable signatures in the cosmic microwave background, circular patterns where our bubble bumped into another before the collision region inflated beyond our horizon. The Planck satellite searched for such patterns but found none, suggesting either that bubble collisions are rare, that they happened too long ago for evidence to remain, or that the multiverse hypothesis is wrong. But even if the multiverse exists and we can't reach other bubbles, what about our own bubble? Does our pocket universe have an edge where it meets the eternally inflating space or neighboring bubbles? The answer is almost certainly no, because our bubble would have inflated to far larger than our observable universe before inflation ended here. The edge where our bubble meets inflation would lie vastly beyond our cosmic horizon, forever unreachable due to cosmic expansion. The 10th, and perhaps most philosophical barrier, concerns the nature of knowledge itself. Every observation we make, every measurement we take, every physical law we discover depends on light and other signals reaching us from distant regions. The cosmic speed limit and finite age of the universe create an observational horizon beyond which we can receive no information. This isn't a technological limitation, but a fundamental barrier inscribed in the structure of causality. What lies beyond the horizon? We can extrapolate based on physics we understand, assuming the same laws apply everywhere. But we can't verify these assumptions directly. The universe beyond our horizon is, by definition, unobservable. We can hypothesize, theorize, and calculate, but we cannot test our ideas through observation. Science fundamentally requires observation to validate theories, yet vast regions of the universe remain forever beyond observation's reach. This creates an epistemological edge, a boundary not in space but in knowledge. There are questions about the universe we can never answer through observation. Is the universe infinite or finite? Does it wrap around on itself? What specific structures exist beyond our horizon? These questions might have definite answers, but the answers might be permanently inaccessible to empirical investigation. The philosopher Karl Popper argued that scientific theories must be falsifiable, capable of being proven wrong through observation. But how do we apply this criterion to theories about regions we can never observe? Cosmologists grapple with this question when proposing ideas like eternal inflation and the multiverse. These ideas emerge naturally from well-tested theories like quantum mechanics and general relativity, yet their most dramatic predictions might be inherently untestable. Some physicists argue that if a theory makes successful predictions about observable phenomena and naturally implies unobservable phenomena as well, we should provisionally accept the unobservable implications. For instance, if inflation correctly predicts the cosmic microwave background's properties and naturally produces a multiverse, then the multiverse gains credibility even though we can't observe other universes. But not all scientists find this reasoning compelling, and vigorous debates continue. The observable universe contains approximately 2 trillion galaxies, each with billions or trillions of stars, countless planets, and unfathomable complexity. We've explored precisely one planet in detail, Earth, sent probes to a handful of others, and observed the rest from afar. The Voyager spacecraft, launched in 1977, are humanity's most distant ambassadors, now in interstellar space over 14 billion miles from Earth. Yet they've barely begun to leave our solar system's gravitational sphere of influence. The nearest star, Proxima Centauri, lies 4.24 light-years away, about 25 trillion miles. At Voyager's speed, reaching it would take over 73,000 years. The center of our Milky Way galaxy sits about 26,000 light-years distant. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. The edge of the observable universe is 46.5 billion light-years distant. These scales are so vast that numbers become meaningless. We can write them, but not truly comprehend them. Throughout human history, we've pushed boundaries and reached previously unreachable places. Polynesian navigators crossed vast oceans in canoes, European explorers circumnavigated the globe, astronauts walked on the moon, and robots traversed the Martian surface. Each generation has expanded the sphere of the known, venturing into uncharted territories. But the universe's edge represents a fundamentally different kind of frontier, one that recedes as we approach, forever beyond reach, regardless of technological advancement. This isn't a counsel of despair, but an invitation to perspective. The observable universe alone contains more wonders than humanity could explore in billions of years. Every galaxy harbors mysteries, every star system potentially hosts worlds with unique stories. Every corner of space reveals phenomena we're only beginning to understand. We haven't exhausted the marvels within our reach. We've barely begun to explore them. The Kepler Space Telescope, operating from 2009 to 2018, discovered over 2,700 confirmed exoplanets by observing tiny dips in starlight as planets crossed in front of their suns. The Transiting Exoplanet Survey Satellite, or TESS, continues this work, finding potentially habitable worlds orbiting nearby stars. The James Webb Space Telescope now analyzes exoplanet atmospheres, searching for biosignatures, chemical signatures that might indicate life. These discoveries illustrate that we don't need to reach the universe's edge to find profound mysteries and potential answers to ancient questions. Is life common or rare? How do planets form? What conditions allow chemistry to become biology? Are we alone? These questions remain open, and the answers lie within the observable universe, potentially within our own galaxy. We're living in the golden age of discovery, finding new worlds at an astonishing rate. The search for extraterrestrial intelligence, conducted by projects like SETI, using radio telescopes to scan for artificial signals, reminds us that the cosmos might contain other observers asking the same questions we ask. If intelligent life exists elsewhere in our galaxy, they too would face the impossibility of reaching the universe's edge. They too would contemplate cosmic horizons, wonder about what lies beyond, and confront the same fundamental barriers inscribed in physics. Perhaps every civilization that achieves scientific understanding eventually realizes this truth. The universe has no edge they can reach, no boundary they can cross, no final frontier beyond which nothing exists. This realization might be universal, a cosmic truth that binds all conscious observers regardless of their origin or nature. We share with hypothetical aliens not just the stars, but the same fundamental constraints, the same unreachable horizons, the same mixture of wonder and limitation. The nature of these barriers also reveals something beautiful about the universe's structure. The cosmic speed limit protects causality. Cosmic expansion gives space its geometry. Inflation seeded structure formation. Dark energy drives the universe toward its ultimate fate. Each barrier that prevents us from reaching an edge serves other purposes, playing essential roles in making the universe habitable and comprehensible. The cosmos isn't designed to frustrate exploration. These features emerge naturally from the laws of physics. Consider what a universe without these barriers might look like. Without the speed of light limit, causality would break down and physics would become incoherent. Without cosmic expansion, gravity would collapse everything into a single point. Without inflation, the universe would be wildly inhomogeneous, making galaxy formation impossible. Without dark energy's acceleration, the universe might recollapse before life could evolve. The very features that make edges unreachable also make existence possible. This suggests a deeper principle. The universe is fundamentally comprehensible despite being fundamentally unbounded. We can understand the laws governing cosmic evolution even though we cannot observe or reach the cosmos in its entirety. Mathematics and physics give us tools to extrapolate beyond the observable, to reason about regions we'll never visit, to grasp universal principles despite our local perspective. Albert Einstein famously remarked that the most incomprehensible thing about the universe is that it's comprehensible. Why should mathematics, abstract logical structures invented by human minds, describe physical reality with such precision? Why should experiments in terrestrial laboratories reveal laws that govern phenomena across cosmic scales? This mystery deepens when we realize that we're using observations from one tiny corner of existence to infer truths about the whole. The standard model of particle physics, developed in the mid-20th century and confirmed by experiments at CERN and other facilities, describes matter's fundamental building blocks and their interactions with extraordinary precision. This model, tested to 1 part in 10 billion in some cases, appears to apply universally. Spectroscopy of distant galaxies reveals the same chemical elements we find on Earth, governed by the same quantum mechanics, interacting through the same forces. General relativity, tested through GPS satellite corrections, gravitational wave detections, and countless other observations, describes gravity from solar system scales to cosmic scales. The same equations that predict how light bends near the Sun also explain black hole mergers and cosmic expansion. This universality of physical law, the assumption that physics is the same everywhere, underlies all cosmology. Without it, we couldn't say anything about distant regions. But we should remain humble about this universality. We've directly tested physics only within our observable horizon under conditions that represent a tiny fraction of possible environments. Perhaps in regions beyond our horizon, different vacuum states produce different physics. Perhaps in the extreme conditions of the Big Bang or inside black hole singularities, our current theories break down completely. The universe might be stranger in its unreachable regions than anything we've imagined. The question of what the universe expands into deserves deeper examination because it encapsulates common misconceptions about cosmic boundaries. When we say the universe is expanding, we're not describing expansion into pre-existing space. Space itself is what's expanding. There's no outside for the universe to expand into because space is the stage on which existence unfolds, not an actor on a larger stage. Imagine an infinite rubber sheet with a grid drawn on it. If you stretch the sheet uniformly, the distances between grid points increase, but the sheet doesn't expand into anything. It's the distances themselves that grow. The universe's expansion works similarly, except it happens in 3 dimensions rather than 2. Galaxies act like grid points, with space between them stretching uniformly. The galaxies themselves don't expand because gravity and electromagnetic forces hold them together, but the space between galaxy clusters genuinely grows. This expansion leaves a distinctive signature, redshift. As light travels through expanding space, its wavelength stretches along with space itself. The more space the light crosses and the more expansion occurs during transit, the more its wavelength increases. Astronomers measure redshift by examining spectral lines, specific wavelengths absorbed or emitted by atoms. Hydrogen, for instance, emits light at 656.3 nanometers in the red part of the spectrum. In distant galaxies, we observe this same line shifted toward longer wavelengths. The most distant galaxy confirmed by the James Webb Space Telescope so far, JD's GS Z13-0, has a redshift of about 13.2. This means the universe has expanded by a factor of 14.2 since the light we now observe was emitted. Wavelengths have stretched to 14.2 times their original length. That galaxy, observed as it appeared just 325 million years after the Big Bang, is now about 33.6 billion light-years away due to expansion during the light's journey. Understanding cosmic expansion reveals why edge is the wrong concept. In an infinite universe undergoing uniform expansion, every location appears to be the center. From any vantage point, galaxies recede in all directions according to the Hubble law. More distant galaxies recede faster. An observer in the Andromeda Galaxy would see the same pattern we do, a cosmic microwave background with the same temperature in all directions, galaxies receding according to their distance, and a cosmic horizon approximately 46.5 billion light-years away in all directions. This cosmic democracy, the principle that no location is special, goes by the name cosmological principle. Observations strongly support it on large scales. The cosmic microwave background has the same temperature to within 1 part in 100,000 across the entire sky. Galaxy surveys show statistical uniformity once you average over regions larger than a few hundred million light-years. The universe looks the same in all directions and from all locations, suggesting it has neither center nor edge. But let's challenge this assumption. What if the cosmological principle is wrong? What if we live in a special location, perhaps near the center of a finite universe with an actual boundary? This possibility seems contrived and violates our scientific expectation of non-privileged position, but we should examine it. How would we detect if the universe had an edge and we weren't at its center? If the universe had a boundary at some finite distance, we'd expect to see asymmetry in the cosmic microwave background and in galaxy distributions. Looking toward the edge, we'd see fewer galaxies, different redshift patterns, and possibly a cutoff in the microwave background. The Planck satellites' all-sky maps show no such asymmetry. The universe appears statistically identical in all directions to extraordinary precision. Moreover, if the universe were finite with an edge, questions arise about what the edge would be like. Would it be a wall that reflects or absorbs matter and light? Such a boundary would violate our understanding of physics, which knows no mechanism for creating impenetrable cosmic barriers. Would it be a place where space simply ends? This concept leads to logical contradictions. What would happen if you reached this edge and tried to extend your hand beyond it? The science fiction concept of a wall at the edge of the universe makes for dramatic storytelling but terrible physics. General relativity describes how matter and energy curve spacetime, but it provides no mechanism for spacetime to have sharp boundaries. Solutions to Einstein's equations that include boundaries require exotic conditions, like black hole event horizons, which aren't walls but points of no return, where gravity becomes irresistible. This brings us full circle to black holes, which offer the closest analog to an edge that actually exists in our universe. The event horizon of a black hole marks a boundary, not in space itself, but in causality. Cross the event horizon and no signal you send can ever escape. From outside, the horizon appears as a point of no return. From inside, space itself flows inward faster than light, carrying everything toward the singularity at the center. But even black hole horizons aren't edges in the traditional sense. Space doesn't end at the event horizon, it continues inward to the singularity, where our current theories break down. You could cross a black hole's event horizon without noticing anything special at the moment of crossing. Only later, as you tried to escape and found yourself pulled inexorably inward, would you realize you'd passed a point of no return. The horizon is more like a one-way door than a wall. The study of black holes has revealed profound connections between gravity, quantum mechanics, and information. Stephen Hawking's discovery that black holes emit thermal radiation, published in 1974, showed that black holes aren't entirely black. They gradually evaporate, returning their mass energy to the universe over immense timescales. For a solar mass black hole, this evaporation would take 10 to the 67 years, far longer than the current age of the universe. The black hole information paradox emerging from Hawking's work asks what happens to information about matter that falls into a black hole. Quantum mechanics insists that information cannot be destroyed, yet black holes appear to scramble and erase information about what fell in, returning only random thermal radiation. Resolving this paradox has occupied some of the brightest minds in physics for decades, suggesting deep connections between gravity, quantum mechanics, and the nature of information itself. Recent theoretical work suggests that information might be preserved in subtle correlations in Hawking radiation or encoded on the event horizon itself. The holographic principle emerged partly from black hole physics, proposing that all information in a volume can be encoded on its boundary surface. If the universe itself is holographic, then perhaps the cosmic horizon functions like a black hole horizon, encoding information about the entire universe on a two-dimensional surface. These deep connections between black holes, information theory, And cosmic horizons suggest that boundaries in the universe aren't what they first appear. They're not walls or edges, but rather horizons, surfaces that mark limits of causality and information flow. The cosmic event horizon operates similarly to a black hole horizon in reverse. Instead of preventing information from escaping, it prevents information from entering. Events beyond the cosmic horizon can never causally affect us, just as events inside a black hole can never affect the outside. Let's now consider the psychological and philosophical dimensions of confronting unreachable horizons. Humans have always pushed boundaries, explored frontiers, and sought to discover what lies beyond the known. This drive has taken us across oceans to polar extremes, into the depths of the sea, and to the moon. The realization that the universe has horizons we can never cross might seem to limit this exploratory impulse, but it actually redirects it. If we cannot reach spatial boundaries, we can still push boundaries of understanding. Every observation refines our knowledge, every experiment tests our theories, every discovery opens new questions. The frontier isn't a place, but a state of knowledge. The James Webb Space Telescope pushes this frontier by observing earlier epochs of cosmic history. Gravitational wave detectors push it by revealing phenomena invisible to traditional telescopes. Particle accelerators push it by testing physics at extreme energies. The universe rewards curiosity not with simple answers, but with deeper mysteries. We thought galaxies were island universes peacefully rotating. Then we discovered they're merging, colliding, and feeding supermassive black holes. We thought the universe's expansion should be slowing under gravity's pull. Then we discovered it's accelerating. We thought we understood matter. Then we discovered that ordinary matter makes up only 5% of the cosmic energy budget. Each answer reveals how much we don't know. This progression toward deeper mystery characterizes science at its best. Newton famously said, "I do not know what I may appear to the world, but to myself I seem to have been only like a boy playing on the seashore, and diverting myself in now and then, finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay all undiscovered before me." Every scientist throughout history could echo this sentiment. Understanding the universe is less like completing a jigsaw puzzle and more like peeling an infinite onion. Each layer reveals another beneath. The emotional experience of confronting cosmic vastness and our limitations within it can be overwhelming. Some people feel diminished by the universe's scale. How can human concerns matter in a cosmos spanning billions of light years and containing trillions of galaxies? But another perspective sees this as liberating and awe-inspiring. We're not separate from this cosmos, we're part of it. The universe observing itself, matter organized to contemplate its own existence. Carl Sagan captured this perspective beautifully when he described Earth as a pale blue dot in a photograph taken by Voyager 1 from the edge of the solar system. That image, showing Earth as a tiny pixel suspended in a sunbeam, reveals our cosmic insignificance. Yet Sagan's reflection emphasizes that this dot is home, the only home we've ever known, containing everything we love, everyone who ever lived, all human triumph and tragedy. Our smallness doesn't diminish us, it focuses our attention on what matters. The same perspective applies to unreachable cosmic horizons. Yes, vast regions of the universe lie forever beyond our reach. But the observable universe alone contains more than enough wonder for countless lifetimes of exploration. We haven't exhausted our own planet's mysteries. Ocean depths remain unexplored, species undiscovered, geological processes not fully understood. We've barely begun to explore our solar system, let alone our galaxy or the wider universe within observational reach. Moreover, the barriers preventing us from reaching cosmic edges emerge from the same physics that makes existence possible. The speed of light, Cosmic expansion, inflation, dark energy, these aren't arbitrary obstacles placed to frustrate us. They're fundamental features of reality, essential to the universe's structure and evolution. We exist because these features shaped cosmic history, allowing stars to form, heavy elements to forge, planets to coalesce, and life to emerge. In this light, the impossibility of reaching the universe's edge becomes not a limitation, but a revelation about reality's nature. We're learning that the universe is stranger, more subtle, and more deeply interconnected than our ancestors imagined. Space and time aren't separate and absolute, but woven together into spacetime. Matter and energy aren't distinct, but interconvertible. Observation and reality aren't independent, but entangled at quantum scales. Each impossibility reveals a deeper truth. The journey from ignorance to understanding parallels humanity's expansion from local to cosmic perspective. Ancient peoples saw the sky as a dome overhead, with Earth at the center of creation. Copernicus displaced Earth from the center, placing the Sun there instead. Then we learned that our Sun is one ordinary star among hundreds of billions in our galaxy. Then we learned that our galaxy is one among trillions in the observable universe. Each step diminished our spatial centrality while expanding our comprehension. Now we understand that even the observable universe might be an infinitesimal fraction of the whole, perhaps one bubble in an infinite multiverse. This progression reveals a pattern. Whenever we think we've grasped the universe's full scope, we discover we've underestimated it. Humility should be our default stance. The universe consistently exceeds our imagination. What we currently believe might seem as quaint to future scientists as ancient cosmologies seem to us. Yet despite this humbling progression, we've achieved something extraordinary. From our tiny vantage point on a small planet, we've reconstructed cosmic history from the Big Bang to the present. We've measured the universe's age, composition, and geometry. We've detected gravitational waves from colliding black holes billions of light years away. We've found thousands of planets orbiting distant stars. We've traced our atoms to stellar furnaces and our origins to cosmic evolution. This achievement testifies to the power of human curiosity, reason, and collaboration. Science is fundamentally a collective enterprise spanning generations. Each scientist builds on predecessors' work, testing inherited ideas and contributing new insights. The cosmic story we now tell emerges from centuries of observation, experimentation, mathematical innovation, and theoretical development. No individual could have discovered it alone. It required humanity working together across time and culture. The tools we've built to explore the cosmos grow ever more powerful. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope, sensitive enough to detect airport radar on a planet orbiting a star dozens of light years away. The extremely large telescope under construction in Chile with a 39-meter mirror will resolve features at Andromeda that are currently invisible. The Laser Interferometer space antenna will detect gravitational waves from supermassive black hole mergers across cosmic distances. Each new instrument opens fresh windows on the universe, revealing phenomena we couldn't previously observe. Who knows what surprises await? Past surprises, cosmic acceleration, dark energy, exoplanets, gravitational waves, fast radio bursts, were unexpected. They emerged from observations rather than predictions, reminding us that the universe contains phenomena we haven't imagined. Future observations will certainly reveal new mysteries, challenging our theories and expanding our understanding. As we approach the end of this journey exploring why the universe's edge is unreachable, let's return to the fundamental question: what does this impossibility mean for us? First, it teaches humility. The cosmos is vastly larger than our observational reach, let alone our physical reach. We occupy one planet around one star in one galaxy among trillions. Our entire civilization is a brief flash in cosmic time, a few thousand years in a universe aged 13.8 billion years. Second, it inspires wonder. The barriers preventing us from reaching cosmic edges aren't arbitrary limits but fundamental features of reality. They emerge from the deepest laws of physics, relativity, quantum mechanics, thermodynamics. Understanding these barriers means grasping how the universe actually works, which is more marvelous than any fictional cosmos. Reality exceeds imagination precisely because it's constrained by consistent laws that produce emergent complexity. Third, it encourages exploration within reach. We cannot visit distant galaxies, but we can study them with telescopes. We cannot observe beyond the cosmic horizon, but we can understand the physics governing those unreachable regions. We cannot travel faster than light, but we can send light itself. Information, observations, knowledge across cosmic distances. The limitations on physical travel don't constrain intellectual exploration. Fourth, it connects us to the cosmos. The atoms in your body were forged in stellar cores over billions of years. The calcium in your bones, the iron in your blood, the oxygen you breathe, all cycled through multiple stars before becoming you. You're literally made of stardust, assembled from materials created in cosmic furnaces, organized by evolution into a conscious being capable of understanding your own cosmic origin. Fifth, it reveals that some questions might not have answers accessible to observation. This doesn't mean we should stop asking, but we should recognize the limits of empirical science. Philosophy, mathematics, and imagination can explore beyond what observation can verify. Different ways of knowing complement each other, offering different perspectives on existence's deepest questions. The impossibility of reaching the universe's edge ultimately points toward a profound truth. The cosmos is fundamentally, gloriously unknowable in its entirety. We can understand its laws, measure its properties, trace its history, and predict its future, but we cannot encompass it completely. There will always be unreachable regions, unanswered questions, mysteries beyond our horizon. This isn't a failure of science, but a feature of reality. This unknowability creates space for wonder, which might be science's greatest gift. When we look at the stars, ancient light, from distances measured in light years, emitted by fusion furnaces converting hydrogen to helium, revealing galaxies containing billions of suns, many with planets where the conditions for life might exist, we confront the magnificent strangeness of existence itself. Why does anything exist? Why these laws of physics rather than others? Why does the universe permit observers to arise and contemplate it? These questions might never have final answers, but asking them connects us to every human who has looked up at the night sky and wondered. Your questions are universal, literally. Any conscious beings anywhere in the cosmos would ask similar questions, confront similar horizons, wonder about their place in existence. We're bound together not just by shared atoms, but by shared curiosity, the cosmic imperative to understand. As you go about your daily life, remember that you carry the cosmos within you. Your thoughts arise from electrochemical processes in neurons, which themselves are made of atoms forged in stars. The energy powering your metabolism ultimately comes from the sun, itself a continuation of the fusion that began in the early universe. You're not just in the universe, you are the universe, a local pattern of organization temporarily maintaining itself before returning to the cosmic flow. The next time you see the stars, know that you're looking across space and time, seeing light that left distant suns years or centuries ago. You're observing a universe with no center and no edge, expanding in all directions, carrying galaxies away from each other while cosmic expansion races faster than light can travel. You're witnessing a cosmos you can never fully reach, fully observe, or fully understand. Yet you can grasp its fundamental laws and your place within its grand story. If you made it through this entire cosmic reality check, you're exactly who I make these videos for. Subscribe for more mind-expanding journeys through space and time, and please give a thumbs up. If you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we will never leave the Milky Way. In this video, discover the real science behind our cosmic confinement and why intergalactic travel is impossible, not just for us, but for any civilization. See you there.